And so while he does that, I'll just say that Dr. Sebastien Tilmans is the executive director of the Codiga Resource Recovery Center at Stanford University, a testbed facility dedicated to accelerating the scale up of innovative resource recovery systems. And prior to joining Stanford, he worked in the process engineering group at Oceanside Wastewater Treatment Plant. Did they name that after George Bush? There was threats, I think, at one point. But anyway, for the SFPUC, he was a Fulbright Scholar, an NDSEG Fellow, and an EPA Star Fellow, and is a licensed professional engineer in California. So I think I've said this a few times, but without further ado, take it away. I will stop my share and
all right. I find myself in the dubious position of being presenting close to 5 o'clock on a Friday, but hopefully I can appeal to all of your interest. Before I get going, can you see the correct slides, or do you see a presenter mode?
Presenter mode.
All right, so now we should be good.
Yep.
All right. For those of you who haven't met me before, I'm Sebastien. I run the Codiga Resource Recovery Center at Stanford University. We are a pilot scale testing and demonstration facility dedicated to helping accelerate the adoption of new technologies for resource recovery from waste. This is a picture of our facility on Stanford's campus. And to give a quick overview, kind of a rough process flow schematic of how our facility is set up, we pump wastewater out of one of Stanford's sewer lines. That sewer line serves the residential part of the campus mainly, and a few dining halls. So you could think of us as a community plant with a few restaurants. We put that wastewater through 3 different treatment processes: a grit removal step, a microscreen to emulate primary treatment, an anaerobic secondary treatment system to emulate secondary treatment. And we plumb each of those streams of water, those different qualities of water, past a set of test beds and a sensor test station where other technologies, other pilot scale testing systems can plug and play to test their technologies in a very low risk environment, because all of our effluent goes back into the sewer and flows down the pipe to the Palo Alto Regional Water Quality Control Plant. So this is a very low risk scenario in which you can test new technologies at a scale of thousands of gallons a day. So that's one of our key missions, is research and development, bringing forward the technologies of tomorrow. And another very related mission is to educate tomorrow's water leaders. So here's a variety of different pictures of students and postdocs, including undergrads, grads, and postdoctoral scholars, learning the nuts and bolts of what it takes to assemble and maintain and operate a wastewater treatment plant, from fabrications to troubleshooting pumps to calibrating instruments and to unclogging things when they get clogged. Some of the past projects that we've had at Codiga Center, and some of these we've had the chance to talk about at previous Sustainable Silicon Valley events. We collaborated with Epic Clean Tech on providing them with biosolids for them to test some of their innovative technologies on solids oxidation and conversion into a soil amendment. We worked with a company called Effluent to test a membrane aerated biofilm reactor. That's the picture you see there, a 20-foot shipping container that we tested at Stanford. We also worked with a company called WH2O Systems, a spinoff from NASA, testing a reverse osmosis forward osmosis system for recycling of gray water and black water, recovery of water for indoor water usage. And we've done various projects also with stormwater capture and treatment. So that's things that we've done in the past. Some of our current projects that we're working on, this is a picture of some continuously backwashed upflow media filters that we've installed at the Codiga Center. This was a picture during construction. So that's an advanced filtration process. And then that's coupled with, you could couple that with resource recovery, take those solids and convert them into energy. We're collaborating with a company called Micromedia Filtration on the filtration part, and a company called Gate 5 on investigating the potential for resource recovery. So, and this is we just got a new grant from the California Energy Commission, where we'll be helping to deploy a system of this in Southern California. We're also testing innovative technologies for automation with a company called Plexus, or a technology called Plexus, that this is really a spin-off from another startup called Bioforce Tech that's done some really, really cool work at Silicon Valley Clean Water. And we also have some sensors and water quality analytics being tested, collaborating with a company named Ketos on that. So a variety of different irons in the fire at the Codiga Center. And I wanted to feature in particular one on COVID tracking in the sewer. So I know Professor Cara Nelson spoke earlier in this conference on efforts that are going on at Berkeley. At Stanford, there's a multi-agency effort with the Stanford team being led by Professor Alexandria Baim to do daily monitoring and tracking of several wastewater treatment plants in the Bay Area and in Sacramento. So on the map here, you see the sewer sheds of the different treatment plants that are involved in this program. And they're collecting samples every single day. And then those samples are turned around, I think, within 24 hours. And then that information is posted to a couple of different websites. The links are in the lower left-hand corner, wbe.stanford.edu. That's our Stanford dashboard, but also these data for Santa Clara County, all the Santa Clara County plants are compiled on the Santa Clara County website dashboard. And these are results that are used certainly on campus at Stanford. So the Codiga Center is one of the monitoring points that are used to closely assess the situation. And one of the really cool findings there has been that the sewer-based data are very closely associated with incidence rates. So we found that this is a pretty good indicator of what's going on in the wider community. And I want to talk about now another project that some of you may have heard me talk about before, which is the Staged Anaerobic Fluidized Bed Membrane Bioreactor, the SAFE-MBR for short. And this is a process for anaerobic secondary treatment to eliminate the aeration from a typical wastewater treatment plant. This is a technology that's been under development for several years now, started in South Korea, and we built what was then the largest one in the world at Stanford. And we've since been working with SVCW. The way it works, it's an anaerobic membrane bioreactor. We use what's called a fluidized bed reactor as the first stage. And the second stage is a membrane tank where we're recycling biogas through the membranes to agitate them and keep them clean. In the first stage, the fluidized bed reactor, we have a bed of granular activated carbon, and we're flowing water up through that bed to fluidize it. An analogy I often use is you can think of YouTube videos you might have seen where people in these floppy tracksuits jump into a wind tunnel and they get suspended in midair. They're falling as fast as they're getting pushed up by the air. We do the same thing with these granular activated carbon particles, and we grow a film of bacteria, of microbes on each one of those grains of carbon. Those are our anaerobic organisms that do the heavy lifting of cleaning the water. So we've done some tests at Stanford for a few years, but I don't think I've had an opportunity to share them with this community. Some high-level results. This system at Stanford, we found that the technology, the system is able to be energy positive, which is really unique for wastewater treatment plants. Typically, wastewater treatment plants consume a lot of energy, but here we were able to produce the energy content of the biogas. So if you measured the biogas, we measured the biogas, and if you assumed converting that biogas to electricity with typical efficiencies, the power that you could get from that was greater than the power that it would take to run this kind of facility. The caveat was that at Stanford, we found that our effluent COD concentrations were higher than we would have liked. So between 80 and 120 milligrams per liter when operating at flow rates, volumetric flow rates that would be competitive with an activated sludge process, an aerobic process. So relatively high effluent COD concentrations with an influent of about 400 to 550 milligrams per liter. So the people that are not technical in the audience, COD, that's chemical oxygen demand. It's basically a very good measure for how much organic material is in the water. And we were targeting here a concentration of less than 40 milligrams per liter. So we were happy, we were excited about the results in terms of getting something energy positive, but disappointed in the water quality, especially compared to tests that we'd seen in South Korea. But now, something I'm very excited to share with you is the results, some very recent results that we've gotten from a project we've been working very hard on with Silicon Valley Clean Water, the California Energy Commission, and a variety of other partners, including Valley Water. This was a project to scale up this innovation, the Safe MBR, at Silicon Valley Clean Water and demonstrate it there. So over the course of the past several years, we've built that system, and it is now fully operational, processing about 24,000 gallons of wastewater a day. Just to give you a sense of scale, that concrete tower you see in the center is, the inside dimensions are 6 feet by 6 feet by 20 feet tall. So it's a little larger than that once you factor in the concrete. We are currently processing primary influent from SVCW in this facility. And what's really, really cool about what we've achieved here is where this system is also energy positive. But not only is it energy positive, but it's actually achieving United States secondary effluent standards for COD. So at this plant, our influent COD, you can see in brown, has been between 400 and 600. And actually, we used to be working with primary effluent. We switched to primary influent that's filtered. And so our influent quality, our influent concentrations have actually gone up, while our flow rates have gone down. So this HRT is a measure of the residence time of the water in the system. So now the residence time is down to about 5 hours. And our effluent water quality, as we sort of proceeded through startup, has now stabilized right around 30 milligrams per liter. So we're actually at SVCW, we're getting an influent wastewater concentration that's stronger, higher concentrations than we had at Stanford. And we're getting better effluent water quality than we had at Stanford. And it's an energy positive system, which means that you could foresee a future in which centralized wastewater treatment plants, instead of consuming energy, would actually be producing a net surplus of renewable power that could be provided to local grids, which would be just a really awesome, awesome result. But it does raise this important question, which I think is fascinating, especially given what we've talked about a lot at Sustainable Silicon Valley events, which is this question of decentralized versus centralized water reuse and recycling. Here we have two case examples. We have the Stanford case, which is decentralized, where we were seeing at the face of it, roughly the same, what you would expect to be roughly the same kind of water quality coming into the plant. And yet coming out, we weren't able to reach the same kind of water quality that we are at the centralized plant. And there's a big question as to why that is. And we think that there's differences in the nature of that wastewater between centralized and decentralized treatment plants. So centralized wastewater is not the same as decentralized wastewater. One of the things that we're going to be looking into, hopefully in the next couple of months, is to kind of go upstream in the sewer and start trying to understand how the wastewater is changing as it travels through the sewer, because we think this has implications for your treatment strategy and how you might want to deploy these kinds of systems. But in the meantime, we're just really thrilled with the results that we're having here at SVCW. And to talk a little bit about what's coming next, because this is secondary effluent standards, but the next phase of this project is all about taking this water from this anaerobic treatment process and saying, what do we need to do now as the post-treatment process to create the advanced water purification center of the future? So in our in my ideal world, the next advanced water purification facility that a Valley Water or a Silicon Valley Clean Water plant would use would be using anaerobic wastewater and be thus much more energy efficient. So we just installed, see this is a picture here at Silicon Valley Clean Water of the digesters in the background, and a 40-foot shipping container that we just got delivered 2 weeks ago. That has another membrane aerated biofilm reactor. We're going to be testing with funds from the US Bureau of Reclamation and the California State Water Resources Control Boards, the downstream treatment processes to take the effluent from the safe MBR all the way to both non-potable water reuse standards, so Title 22 standards, and for potable water reuse. To explore, really push the envelope of what we can do. So not just thinking about how do we get clean water, how do we get potable water, but also how do we do it and really transform the paradigm to be producing clean renewable energy, more clean renewable energy at the same time. So that's kind of a quick sum up of what we've been up to at the Codiga Center. And I want to emphasize here, I've told you we're really, really excited about the results that we've been having here at SVCW. Those of you who've been following this project know that this has been a long, sustained effort with a lot of our partners. And this is what it takes to do truly transformative, innovative research. And I can't heap enough praise on SVCW, our partners, for pursuing this project and for supporting it and for sticking with it. In addition to all of the things that they're doing, which Kim just talked about, this kind of research is so important for the industry, and yet it's really difficult for a wastewater treatment plant to take on, because their core mission is to keep the water running and to overcome all of these issues with corrosion and systems breaking and capital constraints, et cetera. So it takes quite a bit of vision to pursue this. SVCW has been a really wonderful partner, and we're so excited about what we're learning and what we're going to be able to share with the whole sector. So with that, I'd love to answer any questions you may have.
Thank you, Sebastien. This is really kind of interesting stuff. So you're making your own kind of contribution to the water energy nexus, just in this process. And it's going to be great to see how the shipping container and those different treatment streams, work out. I think you hit on something that's been a theme throughout this, whether we're talking about, groundwater management or everything else, and in that kind of sense of cooperation, it's sometimes the toughest thing to do. And I know, like Silicon Valley Clean Water, they don't have anything else going on, so
yeah, exactly.
But they're definitely have a bunch of different things going. You mentioned even Bioforce Tech and I guess Mango, and we're hearing just in the chat Bob Whitley saying good going and sharing the results. So sending out a cheer for that. I'd like even post Waterpalooza, keep a tight watch on what your how these kind of results are going, because as you say, I mean, this looks like a mode towards advanced purification of the future.
Yeah, we certainly think this has a tremendous amount of potential. and we're thinking about, these results are really promising. We're thinking about what are the ways that we could scale this up even further, prove it out at larger, even larger flow rates. But yeah, we think that this is really exciting.
What is the flow rates that are part of this project?
So our system at Silicon Valley Clean Water is operating at 24,000 gallons per day. That was the design. That was our target flow rate. It's doing so well that honestly, I'd be curious to push it and see how much we can how much we can achieve in that compact footprint, because we're not really even straining the membranes. That's some of the other research. There's a lot of other results that I don't have time to share here, but the system is truly performing exceptionally well. Really exciting. So 24,000 gallons a day, that's still very small within the context of a plant like SVCW that's doing 12, 13 million gallons a day on a dry day, and far more than that on a rainy day. So that's where I think there's still a lot of scope to scale up. I'm seeing a question in the chat from Peter Treckmeyer about what I'd recommend for Palo Alto to do with its sewage sludge. It's a tricky question, because in this case, what we're doing here is anaerobic treatment of the liquids. And the idea with that is that you could increase the amount of biogas that you'd be able to produce, and you would actually reduce the amount of biosolids that you're producing as well, which means that you would probably need fewer digesters to manage the solids that are produced at a plant. So, one way to think about it for the case when running the numbers with Silicon Valley Clean Water, if they have if they need 3 digesters right now, which they don't, but if they needed their 3 digesters, if they implemented the safe MBR at full scale, they would probably be able to remove one of those from service. So they could reduce their capacity by 30 to 50%. And so that's where we think this kind of technology could be transformative for other plants like Palo Alto too. If you don't have solids handling infrastructure yet, or if you don't have digesters or energy recovery systems for your solids, I don't want to imply that Palo Alto doesn't have solids handling infrastructure. They absolutely do. This could potentially kind of change the economics, where something that wouldn't necessarily be attractive could become so, because of the additional biogas production potential, energy production potential, coupled with the reduced footprint that would be necessary.
Well, Sebastien, thank you for this report. This is really kind of encouraging, and definitely want to, as you say, it has all kinds of implications for for treatment processes, through various stages. So, wow.
Absolutely. We look forward to sharing more in the future.